Okay, so the next lesson in the string of pre-IB lessons deals with functions, what you should know about functions before you begin the IB program. So let's establish a couple of big ideas. One is that a functional relationship is one-to-one, in that for every x, there is only one y. For every input, there is one and only one output. So sometimes you'll see a domain, which is the set of all the inputs, and a range, which is the set of all the outputs. And maybe our rule is that f sends the value of x to, I don't know, 2x minus 3. So if x is 2, then f of 2 is just 2 times 2 minus 3, and that's 1. And so you would see the 2 paired up with the 1 like that. And if I wanted f of 5, I would find f of 5, that's 2 times 5 minus 3, that's 7, and you'd see 5 paired with 7, just like that. If this thing is a function, if this relation, this set of ordered pairs is a function, then whatever 2 goes to is the only number it goes to. We could not draw that arrow in. Could not. Having said that, and extending our page slightly, if we had some other function and we used f up here, so we'll just use the next letter of the alphabet and say that g of x is x squared, then I could ask what g of negative 2 is, and that would be negative 2 squared, that's 4. We'd have an arrow that goes like that. But g of 2 is 2 squared, and that's also 4. So here's the reality on functions. Multiple inputs can have the same output, but from every input, there is exactly one arrow. One arrow out, one arrow out. That's how you know that you have a function. Okay, so talking about functional notation, if f of x is x squared minus square root of x, and I want to know what f of 4 is, then I take this 4 and I replace every x with 4. That's 4 squared minus the square root of 4. That's 16 minus 2. That's 14. Sometimes we make substitutions not numbers in place of variables, but other variable expressions. So I might want to know what f of x to the 4th is. And in that case, every one of these x's gets replaced by x to the 4th. So that's x to the 4th squared minus the square root of x to the 4th. I know x to the 4th squared, those powers multiply, so that's x to the 8th, minus, this is the square root of something to the 4th, that's x squared. And maybe we could factor out a GCF, and maybe we could factor what remains as a difference of 2 cubes, but those are things I'm not going to worry about at this time. I am going to say that when you come to class, you should know if f of x is x squared plus 3x plus 2, it would be nice to know what f of 2 is, and what f of negative 3 is, and what f of x plus 1 is. As an aside, if you're looking for f of some number, if you're looking for these folks, then it is perfectly fine to go to your calculator and say, let's graph this thing, x squared plus 3x plus 2. There's my parabola. So when I want to know what f of 2 is, I find x equals 2. I find x equals 2, and I go up to the curve, and I say whatever this y value is, that's what f of 2 is. Now it turns out that that's 12, which makes sense because if I follow 2 all the way up, that does put me at about 12. Just something interesting for you to consider in your homework time. All right, on to this domain and range business, because back over here, we had information about domain and range, and the domain turns out to be the set of all the inputs, and the range turns out to be the set of all the outputs. Now, for most functions, most of the functions that you will study are polynomials. So if you have something like x cubed minus 1, something that looks like this, anytime you have a polynomial, the domain runs from negative infinity to infinity. It includes all real numbers. The domain of any polynomial is all real numbers, the set of all real numbers. There's no number that cannot be substituted into a polynomial. In this case, the range also runs from negative infinity all the way down to positive infinity all the way up. But range does not always go like that, because we could just as easily take a look at x squared minus 1, which looks something like that, and see that, sure enough, the domain is negative infinity to infinity, but the range, now that's different. The range has a bottom here at this y value, which happens to be negative 1, and then the range continues up for all values of y. If it helps you, when you're looking for range, I imagine that over here is some gorilla shining a flashlight on our function, and the function casts a shadow on the y-axis. Where that shadow is from negative 1 to infinity, that is your range. You can similarly think about domain in those terms, because what if we have some kind of radical function, and I take my calculator and I graph the thing and I find out that it looks like this? Well, how do I find domain and range from that? So I consider that there is some gorilla holding a flashlight up here at, that's a terrible looking flashlight, but it's a flashlight at positive infinity, and it's just shining down its light, and so there's a shadow cast on the x-axis from here all the way down. Where is the here? It's at x equals 2, and so we would say that the domain runs from negative infinity to 2. Now we have good reason to believe that, because we know that the radicand, the expression that's under a radical, must be greater than or equal to 0. And if we solve that, we get exactly what is expressed down here. As for range, we know what kinds of y values come out of radicals. The only values that come out of radicals are non-negative values, and so we know that 0 to infinity has to be the range. If you don't like that, then you have to imagine that there is a gorilla holding a flashlight. Oh, the gorilla is holding the flashlight, the light's pointing this way. And there's a shadow cast. Well, it's shining from the other infinity also. And that shadow goes that way. What you should know how to do when we gather is what the domain and range is for f of x is radical x minus 3, and g of x is radical 9 minus x squared. Careful what that looks like. And h of x is 1 over x minus 2. And you might need a picture and you might not for that. You just want to think about what values of x can be substituted and what values of y could conceivably come out. One other thing to think about. Well, two other things to think about. The idea of composition. So let's pretend that I have two functions. We'll have one of them is x plus 4, and the other of them is x squared minus 1. When we talk about a composition, when we talk about the composition f of g of x, f of g, sometimes pronounced fog of x, is f evaluated at g of x. So literally, we take this function and stick it into that function. We take this function and stick it into that one. So we find f of g of x. Did you notice how I said g of x but wrote g of x? Good. So now I have to think about what the f function does. What the f function does is it takes whatever the input is and adds 4. It takes whatever the input is and adds 4. And that does simplify. But when I'm doing a composition, when I have fog of x, that fog means f of g of x, which means I figure out what g of x is and I insert it into the f function. We could say the same for gof. Gof is g of f of x. So what does that mean? That means I'm going to take this function and stick it into that one. I'm going to take this function and stick it into that one. I'm going to find g of x plus 4. So I ask myself, what does the g function do? The g function squares the input and subtracts 1. It squares the input and subtracts 1. But this is the input. And so that's my gof of x. A little bit of algebra. X squared plus 4x plus 4x plus 16 minus 1. Compositions are not commutative. Fog is not necessarily gof. Hey, one more thing. When we talk about the inverse of a function, the inverse of a function is the function such that if you compose the inverse, that's read f inverse, if you compose the inverse with f, or if you compose f with the inverse, you get the identity function. You get x. F inverse is the reflection of f in the line y equals x. So let's pretend that f of x is, just by way of example, let's pretend that f of x is 2x minus 6. If I want the inverse function, f inverse, we switch x and y. Well, there isn't any y. Oh, sure there is. That's a y. So instead of writing y equals 2x minus 6, we write x equals 2y minus 6, and then we isolate y. We get this y by itself. So adding 6 and dividing by 2 appears to do the job. So the inverse function is x plus 6 over 2. And if you don't believe that they're inverse functions, you're free to take your graphing calculator and graph 2x minus 6 and graph x plus 6 over 2, and notice that they are, in fact, images over y equals x. You have two functions that are images over y equals x. Okay? Okay. So what do you have to know how to do? You have to know, let's pretend that f of x is x over x minus 4 and g of x is 5x minus 1. I would like to know some things. I'd like to know what fog of x is. I'd like to know what g inverse of 9 is. That means you have to find out what the inverse function is for g and then evaluate at 9. And then if you're really good, I want to know what f inverse of x is. I want to know what you get if you flip-flop the y and both x's and solve for y. That seems like that would be a fun question for you to do. Okay, so those are things that you should think about in between now and the time we gather again. Looking forward to seeing you when we next meet.